Hello guys, just want to go through a little spreadsheet I developed on analyzing the layout of a aircraft wing. And yeah, my name is Richard, you guys doing from Flight Structures. And yeah, I just want to share my exercise. I was looking for how people will go about design a layup of an aircraft wing, without any software, how it was done in the past. And I tried to think, surely there must be a simpler way without having fancy computer programs, finding element model optimization software. And just kind of tried to figure something out. It's very, very simple, very basic. You will not design an aircraft like this, but it gives a good understanding of how you would look at the load parts of the aircraft and design the aircraft. Now, something to just point out, this exercise is based on what one guy thinks, and in this now there are different guys who stress an aircraft differently, but I'm just in this guy's team. So what you're going to see is that I'm very, very biased to the stress analysis, because this is a stress analysis spreadsheet, right? So what I did was I used an example of a Rafale aircraft, and as you can see in here, I just got some cutaway images from the internet, and also used some information from Wikipedia on the mass of the aircraft. I've used it's got gross weight of 15,000 kilogram and a max takeoff of 24.5, so I've just used 20 just as a rounded number, and I've used a maximum G limit of 9G for this wing design. And basically what I'm looking at is based on this Raymer description of what the critical load case is. The inboard part of the wing is going to be designed, which is where the weight is going to be designed by a maximum wing bending, which is maximum NZ, and also same here, but here you have to have a gust. I suppose you can say there's going to be a roll impact here, but for the purpose of this, I'm just going to use the maximum NZ. So based on the taper ratio of this aircraft, which I just measured by scaling through this picture here and using the wingspan and length data here, I've just guesstimated that the taper ratio is something like 0.2158, and from the Raymer load distribution, that's really this green line here. I just kind of scaled this green line to show if I go from 0.5 to 0, then 0.215, it will just be this curve here. For that load, I've estimated it to say, okay, to idealize it, instead of having this complex curve, I can just represent it with a rectangular section and a triangular section. So yeah, I'm overloading it at the tip here, but I'm underloading it in this inboard section. So overall, my shear force and bending loads should cancel out, and I'll be a bit conservative in my bending, and my shear force will be conservative here, and then it cancels out and it's more balanced here. Okay, the reason for that is if I have a load coming in the rectangular section, my bending moment can be calculated by summing that load and apply it in the middle. And for the triangular section, again, I can calculate that bending moment and then apply that based on a third of the distance from the base, from the back end, or the inboard end. So this is inboard going outboard. Okay, so for this exercise, again, I've looked at how a wing is loaded, and for this purpose, I'm going to say 80% of my lift is coming from the wing. That's very conservative, but that was intentional, because in this case, you can see that more aerodynamic lift is going to be coming from this fuselage, but I don't have any specific data, so I've just assumed that 80% is coming from the wing, which means 40% is coming from one wing that I'm going to be stressing here. So let's just go into the information. In here, I've not actually considered wing torsion, so I've just really considered the wing bending and shear force. For this exercise, like I said, I'm using the I-beam equation. So like I said earlier here, I've used this I-beam assumption, which means that my spar is taking my spar is taking my shear load, and my skin is going to be taking my wing bending. So for that, I need a moment of inertia for my aerofoil shape for my skin, which is my wing skin, and I've approximated it as an oval. I've got some general equation for an oval. Now my oval length is about 90% of my chord, wing chord, and my oval depth is my wing depth. You know, in this exercise I can scale my wing depth based on the aerofoil shape of an F16. I don't have a Rafale aerofoil shape, so I just assume this. It's just an exercise anyway. And I've got that depth to chord ratio of 0.73, and then the oval to chord ratio is 0.9. I've also got a couple of other calculations here where I've calculated that the area of an oval to the area of a rectangle is about 0.785. That's if I use this oval and multiply by just the length times the height. And there's a reason why I did that, because I'm going to calculate my area of my spars, which are spread around that, and they're just similar single rectangles. So I'm going to scale my spar areas by this 0.785, and then my moment of inertia. I've also calculated a moment of inertia ratio of about it was 0.59. So if I had that was a rectangle, and I calculated that section as a rectangle with the same height and depth, and then I calculate this oval, then it's about 0.59. That's just in case to simplify that. If I assume that was a rectangle, then I just need to factor the I by 0.459 and then the area that by 0.785, and I've got the properties of my aerofoil. Okay, so let's get into the actual calculations here. So I'm going to use the baseline. In this baseline, I've used this layout, so I've got about 14 spars here, and then it drops down to 13, and then 9 and 6 and 5. So yeah, you can look at the number of spars. So I've got my number of spars of 14, 13, 9, 6, and then 5, and that's based on station 0, which is at the wing root, to 1, which is at the wing tip. You know, now when I say wing root, I actually mean let me see if I can find that picture again. I mean this section here. So this is the section here that I'm using for my, so it's this section here I'm sizing. Okay, so based on that, I've said okay, my shear force from it's going to be my buildup of load based on my triangle and my rectangular section is going to be building up, you know, just based by scaling on the distance. So my total force that I'm going to be applying is my 20,000 newtons times my acceleration times my safety factor times my 80% wing load, and I've taken half of that 80% wing load, which is just for one wing, and so that's my total force. Based on that, my loads in the rectangular section will be based on this area section here, which is this 2 ratio here. So and then my triangular section will be the triangular part of that ratio. So you can see the area there, that area ratio is 0.48 to 0.475. Okay, so it's roughly about evenly distributed. My wingspan is 4.116 based on my scaling. So so from that I was able to calculate my I've got my chord from the root to the tip, so I'm scaling linearly across based on this ratio. I've got my load bending, so it goes from 0 to the maximum bending moment, which you can see is the maximum shear force here, and then the bending moment is just really a multiplication of a buildup of those force and calculating the maximum bending moment up to that tip. Now we can just check that bending moment calculation and just do a quick check for that. Let me just, we've already got the shear force, that's already total there anyway, so that checks. Okay, so for the bending moment is going to be equal to this force times this divided by 2 plus this force times this divided by 3, and you can see that that's correct. That's the maximum bending moment we have there. Okay, so just delete that. So now for the properties, again, we just assume that this is a aluminium wing. So I've just taken out some aluminium properties from Mill Handbook 5, you know. So then what I did was I've assumed in the calculation, I've assumed that my shear force will be taken in the spar, and then my bending moment will be reacted by the skin. So my moment of inertia is purely based on the moment of inertia of my oval. So my skin is taking the load. Now my lower skin thickness will be based on just pure bending, because that will be in tension. The wing is bending upwards, so my lower skin is in bending. My upper skin will then have that will be the thickness that will be used to calculate the moment of inertia. The upper skin is not used, so it's assumed that it's a constant thickness. My upper skin will be in compression, so my upper skin will then be scaled up further to meet the buckling strength. So the lower skin is stressed by this tensile strength, but because of the compression in the upper skin, I've calculated a buckling allowable critical buckling stress based on this equation here. This equation is based on the curvature of this aerofoil. Now obviously the radius, that R radius here, is going to be quite big, and I've just got a picture here. Let me just see if I can find it here. You can see I've got a big picture to kind of guesstimate what that radius could be, and then that radius will be 5 times the chord in something like that, something like 5 times that chord. So again, I've got that ratio in there again. So I think it's that's the number radius to chord ratio is 4.89. So based on that, I've kind of used to calculate my bending of my compression, critical compression stress for the upper skin, and then also for the shear stress, critical shear stress for the spar. I just used this equation here. It's just a simple spar, and sorry, this one is spar shear equation. Now for the equation here, what you'll see is that I've used this infinite number here of 4.4 for the simply supported and 7.8 for the clamped. Now in my section, this is conservative. I believed in this case I may have used an average of the two of the 4.4, because I could be simply supported. That's probably going to be too. I could use the 4.4 or use the average of that, and I'll just put this number there. Anyway, just an exercise for you can just put that number there to get a different thickness. So based on that, the way what I've done is in here. So I've got my geometry parameters here: the thickness of my upper skin, the thickness of my lower skin, number of spars. So my moment of inertia is just doing the calculation, 0.59 times 0.9, so it's 0.59, which is the 0.59 ratio that I've got earlier on. So sorry, it's the one I had here for this oval. That's my oval ratio, 0.59 to the moment of inertia for an equivalent rectangle. So I calculate the moment of it, and then I've used the 0.9, and then for the area I've used this 0.785, but that's based on 0.95 because that area is going to be a bit longer. So I calculate the moment of inertia of the skin. So my lower skin stress will be just the my over I. My upper skin stress will be similar, but again, it's actually my lower skin stress, which is the same, but now I'm going to scale up my thickness of my skin for the compression, and that will reduce the number of stress. So it's just a factoring up by the new thickness of my upper skin. So my compressive stress in the upper skin will be reduced based on my increased thickness. So if the thickness are the same, the shear stress in the spar is just the so it's the number of spar times the height of the spar based on this chord, and this times this depth here based on this depth, and times this thickness, and then I multiply by this area ratio, which is this 0.785, to say, okay, because the spar is developed is distributed over an oval section, so I've applied them. So my shear stress also refers this 0.785, and so it's my total shear force divided by my total area, which is my depth times my spar shear. Now in here I've removed from my depth, I've removed the thickness of the upper and lower skin, and then I've also removed so the area is just really number of spars times the thickness of spars times the height, which is the depth, minus the 2 thickness of the upper and lower skin, and then it's shear force divided by that, and then there's a factoring of that spar area by this ratio here. So I've calculated my spar shear stress there. Very simple calculations, and then I put my ultimate strength, my shear strength, and then my critical buckling and my critical shear are from those equations that I showed you earlier yes, for the critical buckling of the skin I use this equation, and for the critical buckling of the spar I use the shear equation. Okay, based on that, let me just go through. So yeah, for the upper skin, for the lower skin is an my over I equation. For the lower skin, for the upper skin is just a scaling based on the new increased thickness, and then that's my curvature radius for the to use for the calculation of this critical buckling for the spar. Now these yellow numbers are numbers I'm going to change the thicknesses of to get my RF of 1.001. It's just because when I use a goal seek to calculate these numbers, you know, it comes up with 0.9998 and once above 1, so I made this 1.001. And then what I then did was I then calculated the mass based on some volume, you know, based on some average stress, average distance here. So based on some properties based on the area and then the distance between these 2 points, and then also calculate the mass of the spar as well. So and so the mass of the skin, that's upper and lower skin, and also the mass of the spar, and I calculated the total mass there. Okay, so that's mass of the skin and mass of the spar, so that's my total mass there. Okay, so in here, as you can see, I'm calculating the number of in here I'm calculating the number of spars, and I've estimated that the total mass for this wing will be based on the aluminium. There's no fasteners, there's no like sealants and shims and all of that, so it's very basic calculation just based on these thicknesses. I've calculated the number to be about 256 kilogram, and why then said this, okay, based on that, can I actually improve on this design? Now I'm assuming this aircraft will be an advanced material, composite materials, you know. Now what I haven't done in here, like I said before, I haven't included the torsion of the wing, so the wing load is not actually applied in the center of that wing and bending is, there's a torsion in there, and that torsion will create a shear load in the skin, you know, primarily in the skin, which normally you can use this the equation of the J equation to calculate, but for the purpose of this, the primary load on the wing skin is going to be the bending load. So plus I've already overloaded the skin when I assume that 80% of the load anyway is going onto the skin, so I'm already quite heavy with that. So I believe I've got, what you would normally do is you'll calculate your bending load and your shear load, and then you'll then do a kind of interaction equation to calculate a new RF, but it's just really complicated, so I've not bothered doing that for this exercise. Now this is a very basic spreadsheet. You can expand it and make it as complicated and as, you know, it's just to get people started, you know. So from here you can see that I've got the weight of 256. Now what I did was I actually created a goal seek function. So if I put say 12 spars here, let's just come in here, let's just change this a bit. If I put say 12 spar here and 12 spar here for these last 2 points, you can see that my RF is going to go below 0. And what I did was I just generated a little script. It was a very basic script that does a goal seek, and I think it's that one. It's in here. So there's a little goal seek macro that actually just does a goal seek and runs through the different section, you know. It's just doing a goal seek. You can see to get an RF of 1.001 for this column, and then this column here. So this is for the lower skin and then the upper skin and then the spar. So if I just run that again, you can see that it's come up with new thicknesses to get this RFs back to 1.001, and now my mass has gone up to 200 and my has changed. Let's just go back to home and just increase the decimal points of that. And it's that one, isn't it? Okay, so when I come back here and I put 13 again, and then 13, and then I can come back and play the macro again, and you can see here that the is 255.7. So what I did was, okay, I've looked at this exercise and I've calculated the mass of this part, and I said, okay, if it was an aluminium component, and I wanted to optimize what would be the optimum number of spars that I needed. So I just played around with the numbers and I changed the number of spars at different locations. Again, it's primarily the inboard area, because the outboard area is not actually sized. The loads are quite low for the outboard, and also the outboard area is not sized by wing bending. It's going to be more a stiffness driven design. As you can see here, it goes outboard is wing stiffness, inboard is the bit that we're going to be using the maximum MZ of the wing. So based on that, I've not really focused on the inboard. The inboard part is heaviest anyway. The inboard part is where you will have more of the weight in this part than in the tipping. So based on that, I've kind of changed the number of spars and then asked the macro to give me the go, seek, and played around with it, and I've got that I could reduce the weight of the wing by 3 kilograms or 2 kilograms if I had 9 spars in the inboard, and then reduce it to 8, 7, and then 6 and 5 on the outboard. So again, it's just an exercise. This is not how the guys that designed the Rafale stressed it. They would have used more advanced tools. They would have looked at all the load case combination. They would have had more data to manage. But this is a very useful way just to understand the load path, how the wing bending loads are going to be reacted by the inboard, by the skin and the spars. And just to, again, I didn't use a civil aircraft because that would be even more complicated, because that only has 2 spars, but it then have stiffness along the you will then have stiff, instead of having this multi-spar design, you will have just one stiff spar at the front, one stiff spar at the back, but then you have stringers going down the middle, and those stringers are effectively breaking the panels again, but your shear is there, and then you now have to analyze those stringers separately to make sure that they don't buckle themselves and they provide enough support to the skin. So it's a little bit more complicated, but you can also you can put that in a spreadsheet, and it just makes the spreadsheet a lot bigger. But yeah, so take a look at this, play with it. It's not how you would stress an aircraft by any means, but it just gives you an understanding of what's happening. So what would be good if you want to play with it is to change this to titanium using the optimum design, which this spreadsheet is, and you can then change the properties to titanium, which you can get, and then plug those in and then see if you get a lighter or heavier design. Composites are a bit more complicated because based on your layup, these properties are not constant, so your shear for your layup for your spar will be shear bias, your layup for your skin, so your properties just gets a bit more complicated. So your skin will have more 0-degree fibers, your spar will have more 45-degree fibers to take the shear, and so you can just have a simple property box like this, just a little bit more complicated. So again, that's why I have not used the composite example, but of course with advanced aircraft like the Rafale, then they would have used the composite and come up with the optimum design. Again, another thing you can do is play with this, go and look for an F-22 data, and you can use the information in Wikipedia and just play with it, have a look and see if you can design a better aluminium F-22 wing like I've done here, and just have a bit of fun. It's good to play with this kind of numbers. It just creates an understanding of what's going on in the wing. And yeah, if you have any comments, and please feel free to share, and we can Thank you.